Okay, so let's get started. Welcome to Design at Large. This is week 2. So I am super excited to introduce Dr. Thomas Ball from Microsoft Research. So Tom is a principal researcher and also a research group manager at Microsoft Research. I'll list off kind of a subset of the greatest hits of his accomplishments, both as a researcher and as a manager. And with a super quick personal story that he's already heard because I introduced him 2 years ago. So Tom initiated the SLAM model, software model checking project, which led to the creation of what's called Static Driver Verifier for finding bugs in critical Windows software device driver code. And that's sort of how I knew about his work. Is earlier on in my career, I worked in software bug finding and operating systems. So I knew about Tom's work from there. And actually, he just won a 10-year most influential paper award at ICSE, which is the top conference in software engineering, for a paper that he co-wrote with co-authors in 2007. So this is 10 years later, and this was voted by the committee as being one of the most influential papers for both research and practice for the last 10 years. These are really rare and awesome awards, and this is on a paper called Feedback Directed Random Test Generation. And as he was also elected as an ACM Fellow in 2011, which is one of the top honors in the field of computing, for his contributions to software analysis and defect detection. And as a research manager, he manages the research and software engineering group at Microsoft Research, which has a bit over 24 researchers working in a bunch of areas. I'll just name some of them off right now. So he manages projects in formal methods, programming languages, program synthesis, debugging and testing, program analysis, empirical software engineering, things in the cloud, including correctness and efficiency, cyber-physical systems, big data systems, and the last topic on here, which is the subject of this talk, is on CS education. So before I hand over the mic to Tom, tell a super quick story, which is that I was an intern in Tom's group in 2009, after the 3rd year of my PhD. So I worked for one of the researchers in the group he manages. So he was kind of the manager of the entire group. And I remember, even though he had to manage, 3 dozen researchers, and all the researchers had multiple interns. There must have been like 100 people that summer, but he made it a point, I remember this really clearly, to schedule a one-on-one chat with every intern during the very beginning of the summer and the very end of the summer to kind of orient us and kind of get a wrap-up of what we wanted to do in the summer and what our longer-term goals were in terms of research and life and everything. And I found that was sort of a turning point for me in terms of research, because that was one of the first times I saw kind of the bigger picture behind the vision behind a lot of things. So I have tried in my own way when I have these students to give them these sorts of orientation meetings to kind of talk about these bigger picture things and what they want to do with their careers and their lives, irrespective of the specific research projects we're doing, before diving into detail. So that's one thing I learned from Tom during my summer. So with that, I will wheel away and to welcome Dr. Ball.
Okay, thank you so much, Philip. That's great. It's great to be here. And we in the research and software engineering group, we focus mainly on problems of software productivity, and our audience is generally professional developers. But we've had over the last 6 years really a bunch of work for end users who are not programmers and also beginning programmers. So really, I'm talking about that pillar that's fairly recent for us. We work in programming languages, better tools, better experiences, and so I'd like to share with you sort of a bit about our journey to this idea of physical computing for everyone. So the outline of the talk, I'll talk very briefly about what physical computing is. I have lots of little examples of physical computers here. If you're into computer science and grants, we call it cyber physical systems, which is just so great for loosening the purse strings, or at least it used to be at some point in time. Now it's something completely different. It has to be deep something. But then I'll talk about what we mean about everyone. I can point over here. I should remember, and then I'll tell you. I'll really focus most of the talk on Microsoft Make Code, this platform we've created, how we're addressing physical computing and making it broadly usable. And then talk about how you can get involved too. We have a platform, we think it's good for a number of things, including research, and so I hope to interest some of you about that. So physical computing is really about creating a physical system, maybe a little robot, maybe a sensor that monitors whether somebody is coming into your office and taking your M&Ms or whatever, but that physical system is governed by computation. It's governed by a computer that has to react to sensors, take some state transitions, maybe communicate to the cloud, and then maybe do some actuation. So that's sort of physical computing in a nutshell. The other way to think about it, sort of more operationally or in terms of the tech, is that it's projects that use microcontrollers. These are the low power, sort of underpowered chips that have small amounts of memory, but can be embedded inside washers and dryers and toasters and even in a pen, right? And so these microcontrollers are the basis of projects, embedded systems that transduce or translate sensor input into a software system and then use that to make decisions and actuate controls, motors, servos, or lights. There's been study around physical computing and its use in education, and the idea is by leading with making something, whether it's like a wearable, a fashion statement that you're going to pin to your clothes, or something you're going to use on your bicycle to create a brake light. The first aspect is to create something of your own design and thinking about it, and then as part of that learning, what is a circuit about? What is a processor about? How do I control, what's GPIO? How do I control pins? And what's this thing called coding that I need to do to make all these components work together? So that's also why we sort of stress that it's make code. First, we want to make something, and that is led by the domain of interests. Within physical computing, many domains, from robotics to health sensors, wearables. So there's really sort of a design first principle here, where the domain is first, and we want to make the coding. The coding is part of that equation. So how did we get into this? So we had been doing some work on a project called Touch Develop, and the idea of that project was very simple. We loved programming our 8-bit computers when we were growing up, and the idea was you created apps for the computer. On the same computer, you're going to run the apps. But with smartphones, you had to get like a PC or a Mac or whatever and code in a complicated environment. So we worked on Touch Develop, which was the idea of syntax-directed programming on your smartphone for creating little scripts. But those scripts had access to all the cool sensors and all the media library and the sound generation. And so you could like shake your phone to make it play a random song. Teacher's coming, face down, player off, face up, player on. And these sort of things, we took it into the classroom, and it was really cool. It lit up the kids. We got them thinking about reactive systems. Simultaneously, or a little bit after that, the BBC, in the 80s, the BBC actually, with then Acorn Computing, did something called the BBC Micro, which was like an early PC in the UK. And people of my age who learned on Apple IIs in the UK, they learned on the BBC Micro. And for various reasons that I won't go into, the BBC wanted to repeat what it had done with the Micro, but do it with more of an IoT style device called the microbit. So the microbit has a lot more power than the 8-bit computers of Apple II and 6502, and I can't remember what the microprocessor was, but it's got microbit has a bunch of cool tech that's packed in on this little board, which is half the size of a credit card. So what does it have? It has a beautiful high-res screen, which plots in one color. It turns out LEDs, through a little trick, can be used as light sensors too, so you can interleave display and light sensing. It has 2 user-defined buttons, so a keyboard with A and B. It has actually an interface, an edge connector with digital I/O, analog, pulse width modulation, some capacitive touch, and it supports all the standard serial protocols. So you can plug it in, and there are a bunch of partners of the microbit who've made gadgets to plug the microbit into. I didn't bring any of those today. On the back, it's sort of a learnable computer. You can learn what the parts are. So you can learn, oh, that's a processor, and there's a compass and an accelerometer. There's an antenna for Bluetooth Low Energy. You have a full 16 kilobytes of RAM, 256K of flash for the program. You have USB interface on the top, and we'll talk about that in a second. A 3-axis accelerometer, a magnetometer, a temperature sensor, BLE, and all for about, I would say, $6 or $7 of parts. So really cool little device. You can wire it to other things. You can communicate between things, but typically these sort of things are programmed with C and C++ compilers, Arduino, the Arduino IDE, sort of 1980s era text-based programming. So clearly, if we were going to take this, and the goal of the BBC was to give this to year 7 students. So that's 5th graders about age 10 or 11. So just entering middle school. That's an important part of the equation. So in doing the BBC Micro, it was a 1-year microbit. It was a 1-year drop into the UK, where the country had already mandated CS education, and they wanted to put this gift into the schools as a technology component to inspire kids, inspire the teachers, get them working in this sort of IoT style 21st century vision of computing. So that was all well and good. So here's an example, a little video of a fun robot that we made with the microbit. So each microbit it has a little, is embedded in a robot, and this cardboard constructions, this is what we lead with. We lead with, you don't have to go buy expensive kits, you take the classroom materials, you put it together. You do need, for this case, a little servo, right, and learn how to connect the servo up to the microbit for the control. And what does this thing do? There's a neopixel array of lights, very bright, as you'll see. The lights will go on, the LEDs will sense, will do the light detection, and then you'll see what happens, right? So as the light goes through, whoop, the robot's jaws go. This was like the hit at BET in January. And super simple to build and create, to design. You can obviously put your own design sense to it, create the robot different heights, different colors, different teeth, friendly, angry, what have you, and then bring it to life with the microbit, and along the way learn a little coding. So that's sort of the physical computing in a nutshell, and sort of what we first did with the microbit. I haven't showed you the programming, we'll get to that. So the idea of everyone is, I think, harkens back to Microsoft roots. The microbit, we were really inspired by the fact that it was very low cost. You can go out and buy very complicated and cool devices for hundreds of dollars, but these days, thanks to Moore's law, and since the embedded controllers are still riding that, these little devices are getting cheaper and cheaper, and you can pack more and more functionality into them. Someday, somebody said not too soon, the Raspberry Pis will have the power of a data center of today. Okay, yeah, maybe, but they're really getting a lot of power. As I said before, there's a range of these types of devices, from things that emphasize fashion and for wearables. There's more robotics. There's really a wide appeal, and the data shows that the physical computing and having the choice of these devices brings in boys and girls, appeals to a lot of people. There's the maker movement, which is using a lot of Arduino. There's a lot of energy around it. The microbit was focused really on middle school, but we see, and as I go around in high school and universities, there's a lot of use of embedded. There's courses on embedded, and so I think there's also, potential for taking everyone beyond what the microbit did with middle school, and sort of making it simpler. So when I went, I think at Tufts, I heard about a program where they're bringing people from outside CS to program Arduino and learn about how to use Arduino in like health sensing, right? But they're bringing people with no CS background and then subjecting them to C coding. So, you know, there's like a bit of a startup, like 3 weeks to basically learn a tool chain, which is not really the point. And so I think also part of everyone is to try to simplify, if people want to use these devices in more contexts, how do we do that? So let's do a demo, makecode.com, and in a little bit, I will ask some audience participation. So we have Macintoshes here. What do we have? We have a Windows machine. Anybody have a Chromebook? No Chromebooks? Okay. So let's go do a demo. The first demo I want to just show you is how do we get code onto the microbit? How simple is it? And what does coding look like? So with the microbit, we were asked to bring in Blockly, which we knew about. This is a visual programming paradigm based on the innovations in Scratch from MIT. So if we want to do some basic programming, we have some blocks, and we have blocks that will show icons, like that will show a heart. But we want to make it event-driven. So we have an input namespace, and maybe on a button A pressed, you know, we're going to show a heart. And then that's the programming canvas. And then on the left side, we have a simulator of the microbit. And when I click there, ooh, I get a heart. So the first thing is, you know, make it very simple to code and then simulate. And I think in good software engineering, you know, we like to test. And so we build in into the web app a simulator for the device so that you can do basic testing of your functionality, not full, complete, cycle-accurate simulation. Then we might say, okay, on shake, I don't love you anymore, so I'm going to clear the screen, and that's here. Okay, and so shaking is something that, well, you can actually do it here, but there's also a button for it. So you can click, and then you can shake. That doesn't really work so well. And then we hit the shake button. So the simulator has affordances for when we have something like temperature sensing or light sensing where we don't have direct control. Okay, so now we want to put that on a microbit, and this microbit is using something called DAP-Link. It's an invention of ARM, and what that does is it makes the microbit appear as a pen drive. Okay, it's a pen drive that has a very interesting property. It exposes two files, one of which is telling you about the firmware, the other points to the website for the microbit. But the other thing is that it will accept an Intel hex file and flash the memory. So here we're going to get that hex file, and I'll tell you a little bit how we get that. We're going to get it from the browser via some magic compilation process, and we get this microbit untitled, and we drag and drop it, and simultaneously, can you see the blinking light and the copy? It's not the fastest. It has to unpack the hex file. It has to figure out where stuff is. Okay, and there it is. And did I get a heart? And shake it. All right, heart, shake. Okay, and that's great. And now, of course, it's in Flash and it's non-volatile, so we should be good to go. And there we go, shake. Okay, so I'll pass that around. So I was talking there, but you can see in about, you know, a few minutes, we got the code, we dragged some blocks, we simulated, we liked it, we got a download, we did drag and drop. So that whole experience is just based on a web app that is served. It's a static package that comes. Once it's on your computer, you have the whole compiler, everything you need. You unplug the computer from the internet, all what I showed you is going to work, and we use the mass storage protocol to be able to plug the device in. Whatever the operating system is, it shows up as a pen drive, drag and drop. So we tried to make this not just for everyone in terms of making the cost low, but using common, you know, the common parts of the operating system, the web browser, pen drives to make everything work. So I'm getting ahead of myself. So the principles behind Make Code. We want to make it very simple to make and code with physical computers. We start with the Blockly with the blocks. We also, as I'll show you, have JavaScript, so you can progress to more complicated programming. In fact, we use that to even create parts of the runtime that goes onto the firmware. So we allow extensions via that. And the other thing was it's just a web app. Everything is written in TypeScript, which is essentially JavaScript. The experience I show you on Windows, and hopefully we'll prove it in the next demo, it will work basically across any operating system with a modern web browser, because everybody supports pen drives, even Chromebooks. iOS is a little tricky because you don't have the USB, but we have Bluetooth as well on the microbit, so we have some ways of getting code off of iOS. So really, one of the lessons we learned with the microbit was that classrooms are becoming more heterogeneous in terms of the use of computers. And we've also made I won't show this, but we've made the editor very adaptive, so it adapts to tablet, it adapts to smartphone. So you can even do the drag and drop programming on smaller screens. And that was something that came out of Touch Develop, because with Touch Develop, we had to start with a screen this small. So we've always been thinking about, well, can I edit, can I use, and you would think, who wants to do that? But you're on the bus and you got a little piece of code and it's got a bug and you can still like drag and drop and simulate even there. So it's sort of nice to be able to do that. We kept that part from Touch Develop. The other part is it's a real system with well-engineered, a bunch of layers. As you'll see, there's more than just making a heart and clearing the screen. There's GPIO, there's Bluetooth, there's the ability to do robotics, richer physical computing systems, go to more expressive languages than the block language with classes, and also to bring in data and concepts of machine learning, because these devices are using sensors interacting with the environment. So start simple, low floor, high ceiling. That's where the design space is. So there's a number of innovations that I could talk about. I'm really going to just focus on the top two. One is the design of the web app and sort of the end-to-end experience in the programming. The idea is you should never invoke a C or C++ compiler for user code, ever. Right? Because you don't want to install one and you don't want to send text over the internet to a compiler that might not be there. And then the other part is full compilation and linking, even against C++ compiled binary in the browser. So got to go to machine code. We don't have a VM running when we have. We are on we're on Arduino Uno now with 2K of RAM. We're not going to put a VM there. So we actually compile all the way to binary in the browser. And we leverage TypeScript. How many people know about TypeScript? I think JavaScript plus some types. And we use TypeScript to mediate between the world of the hardware manufacturer, the device driver writer who's very comfortable with C and C++, and the world of the beginning programmer, which is Blockly. So we automate a lot by using TypeScript and having a path down to C++ from TypeScript, and also using TypeScript as a sort of descriptor for generating the blocks and that gives us a way to extend our runtime, which I'll show you. There's other innovations in there. Lancaster University did our runtime, which is this small little operating system, the component-oriented device abstraction layer. And then we also did some work on which I'll demo, but I won't describe the technical aspects, to make flashing over USB much faster. So this is what we're doing. We're really doing a platform with partners. And so within the web app, you have two editors for Blockly and JavaScript with round tripping, and I'll demo that. It's really core TypeScript. So the TypeScript is the language of the web app, both in which the web app is implemented, as well as what we use for all the IntelliSense in the browser and all the goodness. Within the web app, you have the simulator on the left side of the screen and a full compile chain down to and linking against a runtime. So the whole web app is parameterized by some notion of a runtime, which is specialized to a particular device, but that runtime has common abstractions like buttons, pins. So if you see a pin on the microbit and pins here, the way you access the pins is the same. And so the idea is there's diversity in the devices, but we have common idioms for accessing I/O, just like Arduino, right? There's a standard API for standard components, and then each partner can have specialized extensions as well. So let's, so the microbit, what happened with the microbit, they're our biggest partner right now. Is the BBC started it, but the whole idea was to set up a nonprofit, which they've done, and that nonprofit has been taking the microbit from the UK out to the world. So it's available in North America via resellers, Adafruit and Spark Fun. It just went into India. It's been in the EU for the last year. So they're the ones who are doing the hardware. They're also bringing together the partners, country-specific partners who are doing content. We do our own content, but they're taking some of our content, developing more. So you can visit microbit.org, and then makecode.microbit.org is actually, we're running that for them. So it's a white labeled website, and we have now actually 6 partners. That just shows 3 here. So yeah, let's go back to the demo. And for this, audience participation, because there's nothing like doing it live. So this is the Adafruit Circuit Playground Express. We said we had Windows, we have a Mac somewhere, 3 Macs in a row. Eeny, meeny, miny, mo. Do we have another type of computer? Is that it? Or anybody else who wants to try? Okay, over here. You can, we'll share, and you can keep these ones and hand them around and use them in the design lab. So you'll get a chance. Okay, so let's take a look at, let's go back to a browser. So find yourself a browser, makecode.com. So you can see our partners here. In fact, some of our partners are not physical computing. We actually have a coding experience for Minecraft. Down here is our first robot, which is from Wonder Workshop. We have some other partners. Chibitronics is really into paper circuits. So you take, you have like copper tape, and you make circuits on paper with lights, and then we have a controller here that is programmed with MakeCode. So if you click on Adafruit, it'll go to makecode.adafruit.com, and you'll see a familiar looking UI, but with a different device on the left. Ooh, oh my goodness, that's a really complicated program I wanted to show you later. So let me just save that, and I will just reset. Don't worry, you won't see that. You should see something like this. Okay, so just to tell you a little bit more about what you're seeing in the graphical user interface, typically we have at the top, we have the categories, which are the device-specific APIs. So for the Adafruit, you have a beautiful ring of sensors. We have a very simple block that lets you just program each light on that directly. These are neopixels, so you have this is very simple use of the neopixel, but here we have just a visual representation where you can click on and then see the pattern come over here. Right? So we design the APIs in levels. We usually try to have visual blocks taking advantage of Blockly like show ring, but then we have other things we can do. We can show an animation. This is a more complex block in terms of its behavior, but we get a nice little use of the neopixel there. And so these things, these blocks are really layered, and so we have sort of the high-level abstract ones at top, and then as you move down, we get more programmatic control. So, for example, we have a notion of not a turtle, but a photon. So the photon is this one-dimensional being that lives in the circle and moves around, and so you can just move the photon around, and with the photon you can make programmatic animations. Input, we follow Scratch. We have, and you saw this with the microbit, we have event handlers. So everything is running concurrently here. I can do something concurrently with showing the animation in the forever block. I'll just actually get rid of that for now. So button A there now is going to start my show animation, and it's going to run it for 500 milliseconds. So that's sort of the blocks. When we click on JavaScript, we compile down into essentially TypeScript, and it gets a little more verbose, right? We have a namespace, we have the input namespace. Within the input namespace, there's a bunch of things you can do. So once you're in the JavaScript editor, it's actually the same editor that's in VS Code. It's called Monaco. Eric Gamma did it. He's the guy who did Eclipse in IBM. So this is a fully featured editor, which we've taken some of the pro dev things out, but there's still IntelliSense. And one of the interesting things we did, I don't know if you noticed, we still have the categories from Blockly on the left. So one of the things that I noticed when I was programming in these dual mode editors was that as soon as you went from the colorful blocks with the categories to the programming to the text area, you lost the categories. But I want those categories. They were helpful, and I don't always learn IntelliSense immediately. So for example, we have a block, right, for those, and those blocks correspond one-to-one. So in the JavaScript, we have many more APIs, but for the categories you've already learned, we have a one-to-one mapping, right? So there's everything that you knew in blocks is here with quite a bit more characters and ability to make mistakes. But there's there, and I click there and I get that. So on loud sound here, maybe I can stop all animations, and there, yeah, there's my first error. It's not inside, right? Okay, and then I can go back, and hopefully it's gonna work. Yeah, actually everything works, and this was another sort of little innovation. TypeScript and even JavaScript now has classes, so I can write classes. I can write a class foo, and I can say let x equal new foo. Okay, and what's gonna happen to that? Well, I don't know, but actually we do know. Everything gets converted back, but you see the gray blocks? Oh, and there's a little design problem, overlap. See, onStart has some code, but that code's not editable. So one of the other innovations was always bring the code back, but not all the code is editable. So we preserve it, we round trip it. If somebody does something more complicated, we can still run it. When you run the blocks, it'll actually execute the code back on the TypeScript side, because that's how the compiler works, right? Okay, so let me just stop there, and let's just run this guy for, I don't know, a little bit longer, like 10 seconds. Right, on button A, click on loud sound, stop all animations. Okay, now we download again, and this time I have to hook up my own device, right? I have the Circuit Playground, and I hook it up, and again, through the magic of the bootloader, it appears as a drive. But this, and if it didn't appear for you, you double click on the little reset button in the middle, and if you get all green lights, it means it's ready to receive a program. But we invented a new format. So check out how fast this this copy is with respect to what you saw before, which was, I don't know, that was about 8 seconds, I think. So there's Circuit Playground, there's my file, okay, and here's the copy operation. Okay, done, right? So that new format and a bunch of firmware just made it almost instantaneous, right? And now the A button is there. Oh no, it's there. Ah, loud sound. Yeah, it stopped. Okay, so I don't know if you saw that. It didn't clear. Okay, quiet. Loud, and it stops the animation. Okay, so that's the Circuit Playground, just to show you, same basic programming experience, because we use the new firmware, super fast copy, this board is a really fun board because it has these beautiful lights, and it has a speaker and a microphone. It doesn't have the networking but it does have, actually it has a infrared transmit and receive. So it has limited networking, fairly noisy. So let me take a little break because I'm just like running really fast here. Are there any questions about what you've seen so far? Wow, okay.
So when you have students using it, how many of them actually go into the code editing part?
Yeah, so the question is, who actually goes to the JavaScript? Right now, it's about 8%, and then most of them come right back. And they've been trained well by things like code.org and a lot of these editors where they have blocks and then they have a JavaScript view which is not editable. But seriously, I think a lot of them go there and it's like, wow, that's a different world. It looks different. And so to tell you the truth, we don't see a lot of people on that side. There's the ability to go there, and we haven't really done a lot of work for programmers who want to land there first. I mean, we've concentrated on blocks first, so it's not a big surprise. I don't know what would happen if we, with our usage numbers, if we put JavaScript as the default editor. It might be pretty scary. And we might want to do that as a little A/B, but I imagine in a day we would revert back. So it's there. We've definitely got from the BBC, like around middle school, based on their trials, there are kids who are tired of blocks. They've seen Scratch since they were in 3rd grade, and they're just ready to move on. So I think there is a funnel, and there's definitely people who go there and go, too scary, come back. There has been a lot of work, not a lot, there's been research papers on blocks versus text, and it's interesting. You know, in text, some edits are easier than in blocks, and in blocks, so we see a little of that, like dragging and dropping moving code is like much easier in blocks, because you just take the whole thing and all the syntax moves, right? You don't have to worry about line boundaries and cutting things off. So we see a little of that use of going back and forth, but yeah, mainly it's blocks. Oh yeah. So on the Blockly side, there's not that possibility, but over here we have TypeScript error messages. So and we have a bug. Yeah. So there's a not a very nice error messages, a comma expected. You know, this is the old problem of getting a good compiler error message, and we're just dependent on TypeScript for that. So you get an error message and then you click on blocks and oops. Yeah, so we don't always round trip. So we only do that when you've got syntactically correct code. We do, of course, have undo. So I can get back. Oh, nice bug. I got to file that one. Oh yeah. By the way, yes, we have 3 out in the audience. Do we have success?
I'm still trying to get it up, but
yeah. Okay, so
yeah, I already ran one.
You already ran one. Did we get success on Mac?
Yeah.
Okay, sweet. Okay, 1 Mac. Okay, good. So right. So we have proof that even PhDs can. Even it's so simple that even a PhD can do it. Okay, so good. So good.
It's a strenuous test.
Yeah, it is. So let me dive a little more into the technical details now that we've sort of done at the high level some of the demos. So yeah, TypeScript is this nice language that Microsoft has done, which is really gradual types, which is the idea of optionally typing untyped or dynamic languages. So JavaScript has this notion of objects, and the objects are used in many different ways for functions, for dictionaries, and TypeScript gives, you can add types, interfaces, classes, you can describe objects and their multiple roles, and it just compiles to JavaScript. So it erases all the types, but it uses those types to enable productivity, to enable IntelliSense, navigation, refactoring. And I think those types are also really great to make code easier, because our runtime is fully typed, which means, when we have a function, we know what it does, right? And I think that's really important, even if you have an untyped language, but you had the metadata, so that when you're in an educational context, you have the ability to give more help. And so I think just at the basic level, having a fully typed device runtime, which gives us the knowledge of what's expected, helps us in a number of ways. It actually helps us generate blocks for Blockly of the right kind and shape. And really, I can't say enough good things about TypeScript. It's a really great way, I think, to develop large JavaScript programs in a modular way. But I think also, because it has classes and interfaces, it actually, if you're teaching object-oriented programming, it's got an object-oriented subset. There's 2 ways that people come to JavaScript. They come to it from their web devs, and they love all the dynamic nature of JavaScript, and they eat up every JavaScript framework, and they're not afraid of prototype inheritance and plumbing everything dynamically. And then there's folks who come from C# and Java and C++, and they're used to static type systems. So with TypeScript, what we've done is we take the superset of JavaScript called TypeScript, and we actually restrict it down to more something that's like Java or C#. So the code people actually write and that we surface to actually our hardware partners actually is very much more like a C# subset. And we think that's also, from an educational standpoint, probably not a bad way to start with JavaScript, because in TypeScript, they do type inference. So you can type just plain JavaScript without really knowing it. And because the APIs are typed, all the types flow around and everything sort of works out with the type checker. So in fact, you know, a lot of the code the students will write is very JavaScripty, it's not TypeScripty, but the types are helping in the background. So that's been an interesting point. And you've seen the correspondence. So fundamentally what happens is we define everything in TypeScript, and I'll show you that in a demo, and we generate the block categories from the namespaces. So we have a namespace, a construct in TypeScript input, and we have metadata that says, I want that in my toolbox. And so TypeScript is the ground truth, and we get Blockly from it. So you don't need to know Blockly at all to create a Blockly editor now. You need to know TypeScript. So here's how we expose C++. So this actually, how do we know it's C++? Oh, there's an int there. Very good. So it's not JavaScript. And it has, C++ has namespaces. And within that C++, this is for the microbit, we have a show number function, and we have a bunch of metadata that says, I want to have a block for it, and it's associated with a part on the microbit simulator. And what happens is we pre-process the C++ and we generate all we generate a TypeScript shim called show number, and it takes a comment from the comment in the C++, and it gives us the show number block, right? Notice that the C++ has an optional argument with a default value of 150, but that doesn't show up in the block. So often our blocks are projections of the full glory of the API. In fact, as I said before, when you're doing the categories in TypeScript, you only see exactly what was in the block. But when you're typing with IntelliSense, all of a sudden there's another parameter. So there's like a layering we've tried to do in terms of we have the complex stuff at the lowest level, and then layers and layers and layers until we get to the blocks. Here's a more complicated example where, you know, our great folks at Lancaster University, they love components. They have a component for the microbit and the display and an image. You set the pixel value, and it actually can have a brightness too. And we just want to plot on a coordinate system, right? So we write a C++ wrapper around this stuff that's in the runtime, and then we expose that. Now the interesting part is we can then program against this the C++ function as if it were TypeScript or JavaScript, right? So we can do led.plot, and we can extend the runtime, which doesn't have a plot all function, to have a plot all function. So fundamentally, the device runtime can be a combination of the native C++, and if you want to add extra functions into it, you can sort of do that. And the beauty of this code is, unlike the C++, it actually has stricter type checking on it. So and the data types here are you won't have array out of bound access and stuff like that. Finally, for the simulator, we need to give an implementation to plot that instead of going against the device, goes against the DOM. So we have a namespace called simulator, and within that we say, okay, I've got the LED namespace, and within that I will define essentially a TypeScript function that does whatever is needed on the simulator side. So at compile time, if we're simulating or we're going to the real code, then we have a choice. So as much as possible, we try to lift runtime up into TypeScript to have common code and make the C++ small, but really that's up to the partner about how they want to divide up the code. Okay. So yeah, let me go back to a demo and show you how this plays out, and also sort of the extensibility. So what if I want to make that robot, well actually, let me do something else first. So one of the things we want to do with the microbit is hook up things like these neopixels. So the Adafruit has neopixels built in, but you can buy a neopixel strip and then hook it up to a microbit, okay? And there's going to be code to drive that, but that code isn't here. It's not yet part of the runtime. So we have an add package, and we have a notion of white listed packages, and this is one. It's a neopixel driver, so that's great. Now, where did that driver come from? Well, that driver actually is defined by a GitHub repo. And so that code is pulled out of a GitHub repo and linked into the web app. And of course, we wrote it, and it's whitelisted. So we've clearly got to keep the security of the code. But here's NeoPixel. So how did NeoPixel? How did we surface that? We got all these blocks, and we have some fun stuff that happens when you actually start using the NeoPixels, because as you note, there is no NeoPixel on the microbit, and I alluded to that before. So when we start running this, oops, what happened? So the NeoPixel package comes with extra simulator extension, and we have a notion of breadboarding, and we have a notion of ports on the board, on the main board, and where components need to be hooked up. So for very simple scenarios, we show you the wiring you need to do to get things running. So how does that play out in terms of what I showed you before with TypeScript? So if we go to our little explorer here, this is for the geeks, we see that there's a NeoPixel package here, and if I look in NeoPixel, I see TypeScript. And essentially what I've got here is I've got an enumeration with some names of colors, and it has annotations, so these are going to show up in Blockly because they're annotated. The NeoPixel has a show rainbow routine, right? And you see it has some default values, and it also says I want to have a block, and I'm associated with a particular part. So all this is the implementation. So in fact, we are implementing a lot of the logic for the NeoPixel in TypeScript. However, if you know NeoPixels, you know it's very timing specific. So we actually also have the assembly language. And since we have a full compile chain in the web app, we're also prepared to take assembly, this is thumb assembly, and compile it in the web app. So in this particular case, when we retrieve this GitHub package, we are actually not just getting TypeScript, we're getting assembler, because we don't want C++. There's no C++. If we had C++ in here, what would happen is we'd go and send it to the cloud and ask, has this been compiled before? And generally, the answer is yes, because everybody loves NeoPixels, and someone else has done it before, right? So anyway, that's just to give you an example of sort of the extensibility that we have. So when we go back to blocks and we see NeoPixels, we're really looking at mainly these TypeScript functions. And we can see, here's show rainbow, right? So there's show rainbow, and when we run that, we see the rainbow pop up. And so we get a little simulator of that. Okay, no dynamics, it's just setting it. Okay, so that's sort of that. If you want to play more, you can actually make your own. You can make your own custom blocks without even creating a GitHub repo. So we have a way of just creating a custom set of blocks, and what we do there is we just let you. We just have a special file where you can put the annotations yourself. So for example, you see this my enum 1 and 2 translates into. Oops, wrong spot. Translates into this this pop-up. All right. So when we see an enumeration, and the enumeration is a parameter value, then we do the pop-up. And so we do a lot of smarts based on that, and you can play around and sort of see how that works yourself by doing this custom by editing these custom blocks. Okay, it looks like we're getting down to the last 10 minutes. Yeah?
Yeah.
Okay, so the other thing I want to say is about progression. So Ben Shapiro, we've been working with at UC Boulder. He's great working in CS education, and he said he gives. Sorry?
And at UCSD.
Oh my gosh, so sorry. Yes, wonderful. Yes, I actually did not know that. He's very right, and it's sort of the microbit thesis that, let's make a computer that's networked and cool and like an IoT thing. And he's saying, look, moving sprites around on the screen is fun, and games are still fun, but 2017 computing is heterogeneous, it's networked, it's social, it has all this noisy data. Like, why shouldn't students and even middle schoolers be able to walk up to a screen and say, yeah, I want to make a networked app, and I want to make the microbits communicate, and and why shouldn't we make that entry to these potentially very complicated things have a simple progression to get you started? And then again, peel the onion and sort of say, well, it is a little more complicated, but I think it's a great idea, and so I want to show you in the last few minutes just about how we do networking, and then a little bit about data. So let's go back. So let's do data first. So this is actually the Adafruit Circuits Playground running as a Windows app. When you're in the browser, you don't have access to Serial and you're in a sandbox. So when we're in the Windows app here, we're in the Windows app, there's a bunch of cool stuff. First of all, you don't have to drag and drop files. It just sort of works. Yeah, it didn't quite work. Let's try that again. We may not be doing this demo. Flashing device. Yes, okay. Maybe it didn't work. Okay, I think we've been working on getting that, and I'm just going to try it one more time. There's all sorts of edge cases with the device being there and not being there. Okay, so this has an accelerometer on it, and what I'm going to attempt to show you. So we're taking the code off the web, but it's running inside essentially a shell here, and I have a special way to get at, if I can remember, to get at our new feature. Okay. And I'm sure it's going to be great now. Okay, so what we're doing here is we're forever writing the value of the x-axis of the accelerometer and the y-axis to serial. Okay, if I run that in the simulator and I do the data viewer here, at least I can do this for you. You can see as I sweep in the x, I get a graph, right, of that, and as I sweep in the y, I see the y move, right? And if the full demo is working, I should be able to do that live. We may not see that. Flashing device, very good. Oh, nope, it's too slow, it's gonna fail. And so I don't think this is happening. Oh, okay, so, but you got the idea. We can when the demo gods are with us, we can take streaming data off the device, we can visualize it, and more importantly perhaps is, if I go back to the simulator, we can take that data and then we can do analysis on it. So we can download it to a CSV file, and if we are running, with say a spreadsheet that knows about that, then it'll start up and the data will pop right into it. So there's the data, right? So we want to make it really easy for these devices, whether they're networked or not, to ship data to a home computer where you can do analysis. So that's pretty critical. And I think that's a big deal. The other thing we do with the microbit is just showing you here is we can create controllers. So we have Bluetooth, low energy, but actually we use the stack underneath, which actually just does UDP, to basically just create broadcast. So what's going on here is we're using the accelerometer and the buttons to send data to another microbit, which is controlling the servos on the car. And just to show you, that sort of code is super simple to write. So let me go back quickly here, and in fact I might even have the code because I saved it. Maybe. Or not. Yeah, I blew it away. So what we can do, for example, I'll just do a very quick one. So on button A pressed, I can send via the radio, I can just send a number, right? And so maybe I'm going to send 0 on button A pressed to whoever's listening, and on button B pressed, I'm going to send a different number, right? And then everything's event-based, so I can say, okay, on radio, if I get a number, then what I would like to do is I'd like to branch on that. I'd like to branch on that number. I'm going to put that in there, get myself some logic, and say, okay, if that number is equal to 0, I'm going to do one thing, otherwise I'm going to do something else. So this is a little more complicated, and what do I want to do? Oh yeah, maybe I should just go back and you know, this time maybe I'll do a, you know, I'm happy, you know, and so basically I'm going to share with a friend sort of what my state of the world is, and you know, here I am. I'm not going to put this on the program, but just show you that the simulator actually copes with all this sort of stuff for 2 microbits. Ah, there we go. Boom. So you see we get 2 microbits, and I press button A here, and we get smiley, and I press button B, and it's symmetric. So this one says, yeah, okay, I'm happy too. No, I'm sad. And so this thing just is super fun. It's great for pairs. Once you get 3, it goes crazy because it's just broadcast. But we have a notion of groups. So when you compile a program and download it, it has a group ID that's baked into the, so everybody who gets the same programs in the same group, but you can set the group so you can go snoop on some other group, and it's completely open and unsecure, and that's sort of the point, right? But as you see, it's all just based on sending numbers, so it's sort of low level, but fundamentally, it's all within the event-based paradigm. It's super simple to get, going. I want to show just one more thing that is another way of doing networking without using a network, at least not using a traditional network as we think of them. So if this just popped up today. One of our team members did this for Adafruit, and this gets back a little bit to our partners. So Adafruit has a great site with a learn section, and there's this notion of how fireflies synchronize in the wilderness. Do you know about this? And it's a beautiful little algorithm that they do naturally to all flash together. Because if you're all flashing together, more will come, and you know what happens then? It's all goodness for the population, right? So the idea is to simulate that with a bunch of circuit playgrounds, and so. This also shows off another thing that we do. So we have a partner website here, and our editor is embeddable. So when we want to teach something in the context of a partner, we can write some code, and then we can o-embed it. So here we're basically setting up the clock of a single firefly that basically is blinking, and it's blinking on a regular interval. And the algorithm basically says, I nudge my clock forward if I happen when I'm not blinking to see someone else blink. Then eventually we all synchronize. If our clocks all signal like every so many milliseconds, and then we nudge our clocks forward. So here we have, what we're doing is we're setting all the neopixels white, and then we're using the light detector. So you have to be in a dark space, but it's pretty cool. You can use these sort of natural phenomenon, and then code them up and see how you can simulate it with the microbit. So here's the end result of that. So they're not really in sync, but as they're flashing over time, the four start to really get in sync. So there's just like, once you start to sort of think about the opportunities with sensors and with communication and data, there's just really a long way you can go with these. Of course, we have, we're really inspired by the educators who are taking this and doing new things, but that's part of the partnership as well. So getting people who want to use these in novel ways. And I'm just going to finish up with a pitch for one way to get involved besides just, going out and purchasing these things and using it. which is wonderful. But in terms of making your own sort of make code experience, I think so. One of the things of the platform that we realize is that there's just so much great JavaScript out there that people are doing for many, many different projects. You can find most anything in JavaScript. You even find a lot of C++ compiled into JavaScript with mscript. And so, one of the things that we think of make code as doing is, we can take a JavaScript library out there. If it has some types already for TypeScript, and a lot of the common libraries do, then we get the blocks automatically from make code, and then we get essentially a domain-specific environment. So obviously there's some work to do this, but I think what we've done is create a framework where it doesn't have to be about physical computing. It can be about something else. And so we've started down that road with something called Make Code Labs, and we had an intern of Ben Shapiro's this summer, Annie Kelly, and I just wanted to show you her example of a target which is for augmented reality. And so here you have these markers, right? And there's JavaScript that can just look at your screen, or rather the camera, and identify these markers, and then you can code against it. So in her case, she's got blocks that basically say, okay, here is a visual representation of the marker. When that marker is hidden, do something, right? Now, before we had this, there was a lot of JavaScript code, and you had to go read it, and to get just programming a simple program, you would have to learn a lot. So this is another nice example. And is it going to run for me? It did before. Maybe I have to give it permission or something. Oh, it was so nice. It was a great demo. Try one more time. Oh, maybe it's because I have that. Let me flip it and see if it. Oh, there we go. Okay, so oh wow, it even got the marker. Yeah. Okay, so there's that, and if everything's working. Oh, no audio. It's supposed to make a sound. So whenever that marker is hidden. So what she is doing is she's bringing together augmented reality marker-based with music making, and she wants to help kids prototype musical instruments, in cardboard with markers, right? And now we've got a little designer here, right, for doing that. And so I think, this left-hand side can become, quite rich. You could have an editor, you could have other ways of creating content than the code. So we're really sort of thinking about, how to leverage all the great JavaScript out there and how to make it much more easy to experiment. And again, the idea is not to code first. It's making something, but coding is going to be part of that, and let's figure out a way to make that coding not get in the way. That's sort of the idea. Okay, so I should really finish up. If you want to check out what Annie's done, you could go to makecode.com/labs. I just did the demo. So conclusions, physical computing for everyone, that's where we started. We try to make the programming super simple through magic of software, all the way from the web app to the compiler to flashing and firmware to make that all go as simply as possible. Makecode.com is the place to go play, and everything is fully open source. So everything I've showed you, the whole framework, most of our targets, the microbit, the Circuit Playground's open source, the Lancaster work on the Codall is open source, Annie's work's open source. We're all using MIT Apache. That's a great world to work in, and we love that. So a TypeScript and all the technology I've been showing you, you can get access to. So with that, I'll stop, and thank you very much.